Is that like the peak?
Yes.
Okay.
Yeah.
Okay, so the ridge line, and I guess,
Yeah, but like basically, I was reminder you and the standard time transaction.
Okay, interesting. Okay.
So yes, so if you look at that, this is the intensity. And this is the and you can draw a ridge line of every single something in the entire world. Everything under the sun. You have a ridge line, and then you can evaluate all this. And we have like here, in this case, right, you're not, it's not going to outside. As soon as you hit the inflection point, everything in memory bomb, because there's a big.
Okay, let's get started here.
It's heavier when you read it.
Okay, so we've ended off last lecture talking a little bit about occupancy, right? So I showed you this occupancy calculator, which student pointed out to me is probably dated. The profiler does this for you now in a kind of a more intuitive way. So you can kind of figure out when you're coding up your programs how to right size your thread blocks so you try to maximize occupancy. And that is usually, that and shared memory are the two like first order things you do when you're trying to optimize a CUDA program. All right, let's talk a little bit about memory accesses and DRAM itself. And we're going to go into DRAM in a lot more detail once we get into the hardware side of the class. But even to understand why you need to write CUDA programs the way you do, you need some kind of a 10,000-foot view of DRAM. Many of you will have seen some of this before, some of you maybe not. But I just want to give you a sort of sense of why it's important to, basically structure the accesses of your program. So the first thing to keep in mind is response time versus throughput. This is like a classic undergrad thing that we tell our students in the context of, what do we usually tell you this in the context of in our undergraduate degree? Sorry? Networks is one concrete place. In architecture, where do we usually bring this up? Pipelining, right? Our networks pipelining. Latency is not the same thing as throughput, right? Throughput is not just 1 over your average response time because you can overlap things. If you can do more things in parallel, then your throughput can go up even though the response time remains unchanged. If you help response time, that also helps throughput, but response time is much harder to optimize for than throughput because you can make things wider to get more throughput. At the end of the day, if you're pushing electrons around, physics limits how much the response time can be, okay? And the reason fundamentally for this is that you can overlap, okay? So the average response time may be high, but if you have enough things overlapping, then your throughput can also remain high. And this is true in GPUs and it's true of the memory system. So when we talk about global memory, there are these sort of sticker values of this is how much DRAM you have on your chip, okay? And the way that GPUs achieve this is not by making the responses to memory super fast. The response time is no faster. In fact, it's even slower than on typical CPU memories that have way less memory bandwidth. The way that this is achieved is by making the interfaces wide, okay? Like, the example from, the sort of UIUC notes, which is, this guy, Wenmei Hu, who sort of made this tutorial on GPUs, is a big like dam of water, right? Like you're getting all this memory bandwidth because we're like shoving a whole lot of water at you in parallel. There's a lot of memory requests that can be in flight in parallel and they can return to all of those cores in parallel. In reality, if you don't structure your program well, you don't drink from that whole deluge of data. You're only drinking from a very small piece of it. And so the only way that you can actually use that DRAM that's on the machine is to make sure that you are basically drinking from all of the stuff that you're getting at the same time, right? And the way you code your program has a direct effect on how much of the data that you're reading from DRAM are you actually using, okay? Because the DRAM interface is wide and you'll be able to read a lot of stuff from it, but if you're not using everything that you're getting from the DRAM, then you're not really using that bandwidth, okay? And if you're not careful with your CUDA programming, you can end up just, not using a lot of So many of you will have seen something that looks like this before. Who has seen this before in relation to memories? DRAMs, even SRAMs. Okay, so this is just basic memory technology design. Memory is not a linear thing, despite the fact, it looks that way to a programmer. Memory is actually a rectangular thing. Cores of memory are arranged in rows and columns, much like a matrix. That's how we fabricate these things. You get these chips, right? They have an X and a Y dimension. Now they have a Z dimension too in high bandwidth memory. So what high bandwidth memory does, it stacks memory on top of each other. It stacks sort of, planar memory arrays on top of one another. But we're not going to deal with high bandwidth memory right now. This is just normal memory, okay? Every memory you've ever sort of interfaced with, every DRAM looks something like this, okay? You basically send it a row. There's a row decoder that says what row the data you want is on, and then you'll light up that entire row in that memory core. It goes down into these really, low response time, or at least as low as response time as we can get, things called sense amplifiers that, you're not actually going to wait to read out whether this thing is actually a true 1 or a true 0. I just want to look at the differential between two signals to try to, as quickly as possible, decide whether that cell is 1 or 0. And that's what's known as a sense amplifier. Okay, super low latency piece of analog circuitry that's inside of this digital pipeline to try to get the memory values out of the cells much more quickly than if you just sort of waited for the 1 or 0 to stabilize on their own. The output of these sense amps then can be latched. So basically, think of it like a flip-flop into what we call column latches that will persist. And so when we read out something from memory, we don't read out just the 4 bytes you want. If you did a load to a float, we read out everything that's on that row. And those rows are wide, okay? Hundreds of bits wide, depending on the memory technology you're using. So every time I go to memory to ask for one word, I'm actually reading hundreds of bits out of this memory cell, okay? And then I come down and, let's see. I already have this up. So then I have these column latches. So these are sort of persisting everything that's on that sense amp. And then those go into a MUX. Okay, so this is the internal guts of the chips of the memory, right? So the memory itself, would sort of, the boundary of this would look something like this. And then the pins that come out of the memory, I have far fewer pins coming out of the memory chip than are inside the chip with that internal bandwidth. So I have a narrow interface that is the sort of off-chip data that is ultimately sending the thing back to the processor, CPU or GPU, and it's fed by this wide interface. And the consequence of this is that when you do something that we call open a row, i.e. we read one value from a row, it doesn't take a lot of extra time to read another value that's also on that same row. So there is a huge time commitment to close a row and then open up another one. But when one is already open, it's much less latency to just read another column from that row that you've already opened up, sent through the sense amps, and is latched on those column latches. So if I can have memory accesses that touch one element in a row, and then the next request touches the next element or any other element on that same row, then on a cycle by cycle basis, I can keep my off-chip pins busy. The name of the game in hitting peak memory bandwidth in any system is making sure that all of the off-chip pins are always carrying good data every cycle, okay? So if I have, one of these memory chips, it's advantageous for me to read from not just one column in the memory or one sort of part of the memory, but to read from multiple while that row is open. Questions on this? This is known as a row buffer hit or a row buffer miss when you're accessing memories. Yep.
If we know that we're gonna just read the entire row every single time, technically we don't need the MUX and the column address.
You still do, because this interface is small. This is the pinout that goes between the memory chip and nominally the memory controller.
Can't we make it wide?
You can, but there's consequences to that, because there's still a latency to open a row, and eventually you're going to have to open another row. And then what do you do? Okay. Yep.
Since the memory unit doesn't have any aspect or idea what the type of data it is, does the schedule and GPU, does it try to arrange the data to take advantage of that?
Yeah, that's a great question. So all chips, CPU or GPU, have memory controllers. Okay, when you do a load, we don't really study memory controllers much in any of our classes as far as, before this class. When you do a load, it goes off into the memory system. We study the caches, what happens with coherence, but after it's out of your caching system and you need to go to DRAM, there is a separate element on every chip called a memory controller. That memory controller buffers all of the requests that come from one or n cores that are trying to go in that system. Inside of that thing, there is a scheduler. Okay, a very simple scheduler is just a FIFO. So it just buffers things because you may have deluges of demands of memory that cannot be instantaneously serviced by the memory system. So there has to be the memory controller that buffers it. And there's a whole game in how you order those memory accesses. And this is where things like consistency come into play, right? Because if I have accesses from different threads that happen at different times, and I want to be super aggressive with my memory controller, I just want to pick everything that's on the open row. I don't care about what I've done to the ordering. That is what screws up that's one element that can screw up sequential consistency for those of you taking 666 right now, okay? And you kind of want to do this because when the row is open, I want to read from it. It also makes it more expensive in the memory controller to do something like that because you basically have to do a CAM lookup now. You have to have an out of order scheduler inside the memory controller to try to schedule the accesses out of order to try to hit on the row. So memory controllers themselves are their own little processors. And so there's two things you can do. One, you can play games in those processors with their schedulers. The other is to just give it a better access pattern from the cores, so that way there's less the memory controller has to do. But there is a whole space here in how I deal with my memory accesses once they've sort of left my cache hierarchy and are going off to the memory controller. Good question.
And the memory controller also needs to refresh the entire DRAM every.
Yeah, so the memory controller also has the sort of boring job of like making sure that the DRAM is refreshed, right? You have the DRAM it loses its signal over time, so you've got to refresh every row periodically to make sure that the charge doesn't dissipate. That's what the memory controller does. It does it by initiating reads every row, right? So there's, it has all of the boring tasks of keeping track, like making sure that a DRAM works correctly, as well as arranging all of the memory accesses that are coming from all of the cores. We don't study memory controller design in this class, but elements of it will creep in when we start looking at what's going on in the memory system at a deeper level. Good question. Other questions? Okay. Memory controllers also have to be aware of like all the mappings, right? Because it's on memory controller, you'll have the data maybe in different banks of the memory, right? And you'll need to know where all that is so that way you can direct the physical address traffic to the right place. Okay. So a whole nother layer of translation, like you learn about virtual to physical address translation. Even after you've got the physical address, you have to take bits of that and figure out what bank I'm in, what row I'm in, et cetera. The memory controller does all that kind of stuff. Okay. Okay. So there's two ways that these could work. One is called non-burst, which is not great, where essentially you sort of, this is just a cartoon to sort of show you the relative delays here. So if we look at when the address bits actually get sent to the decoder, so the decoder for a particular row, it takes time. Okay, it takes time for you to actually light up that row and get the values out on the sense amps. And this is, we're bumping up against physics, right? We really can't get it out much faster than they're able to, given the capacities we want in the memory chips. So this is going to inherently take time. Once it's done, then if you're only reading, one burst, so just one, width of whatever your memory interface is, then it would look like this, okay? You would basically burst out, the one sort of, however wide this thing is, right? However wide this off-chip data interface is, you would just burst that out once, and then you would go access the row again, or access another row again, and then burst out another access, which is bad, okay? So that's non-burst. Burst says that I'm going to give you a whole bunch of data, even if you didn't ask for it. Okay, so I'm just going to say, I open this up. I'm going to, over several cycles of your memory system, I'm going to give you some of the stuff that I have on this open row. And I'm going to do that very quickly because I've already got the data on the sense amps, and I'm just going to keep sending you, a bunch of information. And this will basically be what we call the DRAM atom size, is how big the bursts are. That means when I go to DRAM, what is the minimum amount of data that I get back? So even if I loaded from one thread a bool, how much data am I going to get back from the memory system? It's not 1 byte. Okay, it's always going to be something bigger than that. Typical systems, 32 bytes is kind of the minimum you're going to get back from the memory system. And modern DRAM systems aren't always bursty. Like non-bursts, at least in high performance systems, maybe this makes sense in some low end or embedded systems, but if you're trying to put performance, burst is usually the way of doing business. Now, in addition to having this concept of an open row, we also will put more than one bank on here. Okay, this is how we add the parallelism in the memory system. There is an inherent latency in opening a row. We can't get around that. Even if we had a fantastic access pattern where we could just read the entire row, we still then have to wait before we can get the next row open, which means we're going to have dead space on those pins. And that is death for memory bandwidth. You want the pin to have something useful on them all the time. So to try to cover that latency, much like the way that threads cover latencies in GPUs, we don't just have one memory bank that can access those pins, we have multiple. Okay, and so this is a simplistic example where I basically duplicated that same thing so that both of them can sort of timeshare this external pins, right? These are the pins we care about. They are shared between both of these banks, and then depending on which one has data ready, either of them can use the pins to send useful stuff back to the processor core. So if we look at what happens with burst, so burst does one thing, it gives us a chunk of data, not just one single whatever internal element that DRAM has. It gives us multiple of them. But when we go to the next value, there's going to be some dead space. And the only way to get rid of that dead space is to put more chips on or put more banks. And that's what banking achieves. So once you've sort of read out in a bursty way from one bank, you can switch and read out from another bursty way in another bank, which you've already started the access on earlier, right? So you can sort of overlap the access time of all of these banks. And if you have enough banks, then you can clear all the dead space on your pins. And then every cycle, at least one of your banks should have something good to give you if there's enough demand. And you've sort of lit them up. Make sense? Yes.
The DRAM atom size would just be the cache block size of the GPU, right?
It doesn't have to be. It can be whatever. It typically is at least the sector size of the GPU. You guys know what a sectored cache is? Maybe learn this in 5.6. What do they call it in 5.6.5? They call it something else. It's a cache where you don't fill the whole line. You break it into chunks. Vijay Kumar calls it something else. I call it sectored cache. It's another name for it. If you guys remember. Subblocking. Okay. So basically you just have one. So subblocking says, and we'll talk about this more when we look at the caching system in the hardware side of this class. There's two ways that I can get smaller atom sizes in my cache. Okay. One is just shrink the line size. Okay, that's easier, right? So I can go from like big wide 128 byte lines, or I can go down to 32 byte lines, 16 byte lines, whatever. What is the downside of keeping a cache at the same capacity, but shrinking the line size? More tag overhead. Smaller your line is, the more tag capacity you need, because now I have to tag all of those extra things to keep the same amount of data in the cache. A subblocked or a sectored cache is sort of an in-between. What it says is I'm only going to keep the tag data for a wider line. So in the example of GPU, it's concretely 128 bytes. But then my access atom size is going to be 32 bytes. So that means that when I go to the cache and I look up a tag, I will hit on that tag if any of those 32 byte segments that would have been on that big 128 byte one are valid. And then I'm going to have to look at a mask. Okay, so I've got a bit mask that says which of these particular sectors or subblocks are valid for this tag. And the upside here is that I trade tag overhead, which is big, right? It's however big your address, it's whatever number of bits you need to accurately represent the tag, which can be 10 bits typically, 30 bits, 40 bits, whatever, depending on your address space range, to just now a bit mask, a vector of like 4 bits if I've only got 4 sectors in each cache block. Okay, so subblocking is a way to basically get some of the effects of a small block size. So I don't always have to fill in this giant thing. I can fill in just a part of it without paying the huge tag overhead. And GPUs make use of this. Because oftentimes you do really want like a big cache line size, but sometimes you don't, and it's disastrous if you're always overfetching by a huge amount of GPUs. Again, we'll touch on this again later, but the why I went down this road was like, what is typically the atom size? Typically, it's, yes, the cache line size, more specifically, usually the sub-block size. Okay, the thing I need to fill to say that this cache state is now valid. Make sense? Yes.
Do GPUs last level caches ever do prefetching to mask like the column access?
Yes. So they can do prefetching. You know, is it useful? Instruction prefetching is certainly useful, right? Sequential access to instruction and a stride prefetcher makes a lot of sense. Prefetching into the L2, you know, if you have a sequential access pattern, is possible. You know, prefetching is a double-edged sword, especially in a throughput-oriented system like a GPU. Because prefetching is essentially speculation. You're speculating that you're going to need this data. If you're wrong, what's the consequence of a wrong prefetch on a GPU?
You have to go to the CPU again.
No. So I'm talking about prefetching into the L2. So you have an L2, the last level cache in the GPU that's in front of its DRAM system. I think this is what you're talking about, right? And you want to prefetch into there to try to cover latencies. What is the downside? So there's several downsides. Memory bandwidth, capacity, right? Capacity is, you're wasting that line now that maybe could have been something useful, but that's not the most disastrous piece. The most disastrous piece is memory bandwidth. And prefetching is only useful if you get the timing right. And guess what? The timing is super hard when you've got like 144 cores, each of which has 32 independent or 64 independent threads on them, all contending for the L2. So the risk of prefetching in a GPU doesn't usually overcome the reward for like normal data accesses. For instructions, maybe, but instructions usually don't matter because there's programs are usually so small they hit in the iCache super frequently. But the game of prefetching on GPUs is, there's papers on it. It hasn't really gained a huge amount of traction. It's less important because the latency is less important. And if you're wrong and waste bandwidth, it's worse, and you can really hurt performance with prefetching. Timing is hard to work out. Okay, good question. Yeah.
Also, the DRAM atom size is just the width of the memory cell array, right?
No, it's not. It's when I go to DRAM, your data may be spread across multiple cells depending on the physical memory arrangement, right? So it's whatever the memory controller says is the minimum amount I'm going to give you back, which doesn't necessarily mean that it's always on one bank or one chip. Usually it's sprayed across banks. Okay, and we'll see that when we look at like memory, how things are actually laid out on the memory chips is not necessarily intuitive with how you think they should be laid out. Because you can do all these bizarre mappings based on the addresses to sort of map stuff across the banks and chips of your memory system that the memory controller is doing under the hood. Okay. Other questions? In fact, in GPUs, they may not even exist in the same memory controller, right? They may, you know, because you have different distinct pins from memory. So when I showed you guys this diagram, these pins represent something that goes to one memory controller in the system. CPUs will usually have 1, 2, maybe 3, 4 memory controllers at most, because they can't soak up the amount of bandwidth that a CPU can. GPUs will have, you know, an order of, there have been GPUs with like 32, 16 memory controllers. So 16, 32 different discrete pin channels out to those DRAM chips. So when you go get data, it may choose to spray it across whole different memory controllers, which control whole different sets of banks and chips. And again, that's at the discretion of the sort of memory system designer, which in the case of GPUs is the vendor, because they control the whole stack, right? It's not like the CPU where, you know, you're sort of plugging into a DRAM, although the CPU memory controllers are usually now on chip and controlled by the vendor as well. So Intel has their own memory controller, right? And then they just interface with the external DRAM system. So each vendor can kind of curtail their memory controller however they like. memory is dumb, right? Generally, memory is really stupid. It's just like, it's a low margin dog eat dog business where, you know, Micron and Samsung's trying to do some more clever things, but they're all sort of trying to compete with each other, you know, to get the lowest price point per bit. So there's not a lot of like differentiation and, I don't know, ingenuity in that space. Now, I don't want to dump on those companies, but like, you know, a lot of the magic sauce in DRAM, because DRAM has to adhere to these standards, right? So it's like JDEC comes out and says, if you want to sell HBM2, this is what it looks like. They just go build a chip that adheres to that standard and then try to decrease cost as much as possible, because everyone else is going to build a chip that is that same standard. And what's going to differentiate you is how cheap it is. Whereas for, you know, the processor vendors, what differentiates you is your performance and energy efficiency. And there's more games to play there rather than trying to decrease costs. All right. Anyway, that's my tour to the DRAM space. You can argue that PIM and these things are sort of changing that. Maybe it's more interesting, but like, who knows if that's going to work. All right. So let's take a look at, you know, bursts from the perspective of a memory system. So let's take a very simple memory system that only has 16 bytes, right? So this would represent a 4-bit memory system. Like if you had a 4-bit machine, okay, which means you can access a 4-bit memory space, this is what it would look like. Logically, you can take each of those 16 bytes and then sort of chunk them up into you know, chunks of 4 in this case. And you can take any memory space, even a giant one that's, you know, 4 gigabytes, 80 gigabytes, what have you, and chunk it up into a whole bunch of these sections. You can think of this like cache blocks or cache lines in a normal memory system, or in a CPU memory system, but we're not talking about caches, we're talking about bursts. So you can basically cut them up into these sections. Now, the way that every warp instruction accesses this space determines how efficiently we're using the bursts we get back from the memory system. Okay, this is something known as coalescing. Okay, there's a concept of coalescing that you learn in the CPU space about like coalescing things in time. In GPUs, generally when we talk about coalescing, it's coalesced in space, okay, across threads that are in the warp. So in this simple example with my 16-byte memory system, I have 4 wide warps. And if each of the threads in that 4 wide warp is accessing data that is contiguous on the same burst section, that means I can go to DRAM exactly once and get back that whole burst section from everything that was on that same row. Okay, so this is efficient. So I am feeding the memory accesses for 4 different CUDA threads with just 1 memory access. And this coalescing gets done in the core itself. So before it even goes out to your L2, goes out across the interconnect to try to get out to the main memory system, the core is looking at all of the addresses that are being accessed by all of the threads on a particular load or store, and it's trying to group them such that I minimize the number of accesses into these burst sections, okay? In practice, when you have caches, it's, you know, cache lines or blocks, but from the purpose of the memory system, you can think of it like burst sections. So this is nice for the memory system because I have 2 different warps in this example, each of which is only touching 1 burst section, so I'm only going to require 2 memory accesses to service all 8 of these threads, okay? And this is what we call fully coalesced. In contrast to this is uncoalesced. So if I had, you know, 4 threads, each of which is just skipping 1 element in my memory space, then I'm going to have 2 bursts or 2 accesses to the memory system to service this first one, which is uncoalesced. So this is bad because it's sort of accessing contiguous data, but the memory is still going to give me back all of these things I never used. So this represents wasted bandwidth. Okay, because I didn't actually, you know, access things in a very what we would call coalesced way. Another way this can happen is if things are just unaligned with the memory system. So if you span 2 burst blocks, you get essentially the same behavior, even though your threads are accessing contiguous elements. In order to get stuff back from the memory system, you're going to have to load 14, 15, and 8, 9, both of which are not going to be used. So you're effectively now at 50% bandwidth utilization. This one simple thing took your 1 terabyte memory system, because this is what's going to happen, and you scale it up over bazillion threads. You took 1 terabyte and you smashed it down to 50 gigabytes just with this one problem. Okay. Questions? And this is, sort of the number one reason why the memory system ends up screwing up the GPUs if you don't think about how you code up your program. All right, I think you guys have seen this before, I hope, right? 437. Let's see if you still remember the answer. Okay. You guys did this in 437?
Yes.
Good with laundry?
10.
Okay. All right. So answer it. How long does it take each person to fill their tray? What is the response time here?
10 minutes.
10 seconds. Okay. 10 seconds. What is the throughput of the buffet?
Same. One person.
One person every 2 minutes. Right. Same as laundry. I mean, we're assuming that everyone is kind of like, pushy, right? And they're like, oh, he's done with the salad. I'm going to go. It's my turn now. Right. So this is sort of concretely demonstrating with like a layman thing, like the difference between response time and throughput. Okay. And you sort of have to have a grasp on this to understand why the memory system does what it does and why really a GPU does what it does. Okay.
Also, we're assuming in order, right? We can't go out of order.
But it doesn't matter. There's no dependencies. These people aren't dependent. It's not like, oh, if he chooses the rice, I'm going to not choose the salad. Like, no, everyone's going to eat everything in this example. So I don't need out of order. Right? If instructions are nice, I don't need out of order. I can just keep going if I know there's no dependencies. Right? Dependencies are the problem. Buffets don't have dependencies. I mean, I guess maybe one of them's a child, and then the other they're trying to like figure out like what they should get. But maybe then there's a dependency. I don't know. That's probably a bridge too far on an analogy. But all right. Questions? Yep.
Only rice.
I don't know, like 25% of the world. Rice is like the staple of, civilization, man. Like, you don't have rice, you're kind of screwed. Anyway, yeah. Some people eat all rice. What else was in this buffet? Soup, rice, meat, fish. Okay, so if you're like vegetarian, you don't do this. Maybe the soup has meat. So yeah, I don't know. Okay. Actually, that's a pretty intense lunch, right? Like that's rice, meat, fish, soup. Like, yeah, I guess you're not moving fast after that. All right. So that's the basics of coalescing. You guys are going to write code. And the machine is going to try to coalesce. Oh, were there other questions before I stop? I think there was another hand somewhere. Yeah, over here.
If there's what is threads from separate thread blocks trying to access one half of the other half, does that get coalesced?
Yeah, that's a good question. It depends. So there are other mechanisms inside. So I mentioned that this coalescing happens in the core. Okay? So before it even goes out to your element cache. If you have two different thread blocks on two different cores, that can't happen. There are other mechanisms in the system that could allow you to just have one access for that. What do you think that might be? So if it's not coalescing, it's something you've studied already. So the scenario is this. I've got one thread block that's touching one of these bursts pieces, and then another thread block is also touching that same burst piece. Out of the core, they're definitely both going to send the request up the memory system. Sorry? Snooping, maybe, but GPUs don't snoop, man. You don't want to snoop a terabyte a second like that. There's no coherence in GPUs for a reason. What other mechanism might you use if I've got two in-flight requests from two different cores coming up through my memory system? It's in the memory system. Study this in 565 for sure. What are the elements of a cache? What do I need to build a cache? Some hands. Give me any element of the cache. Yes.
MSHR.
MSHR. What does an MSHR do?
It checks for the status.
It checks in the status.
Keeps track of outstanding misses in the cache.
Keeps track of outstanding misses in the cache. What else can the MSHR do? Merge.
Yeah.
MSHRs can merge. So what does that mean? So MSHR, for those of you who forgot, they're super important in GPUs for this reason. So MSHR, miss status holding register. Okay, if I miss in my cache, I don't have the data yet for that block because it's in flight somewhere in the 400 cycles of the memory system. But I might get another request at that same cache for that same address, that same tag. I don't want to just go send another request because that soaks up useful bandwidth. So an MSHR is essentially a tag structure. It's got a bunch of tags inside of it to keep track of all of the in-flight requests. And then it's got some other meta information to say who is waiting on said request. So if I'm the L2 or the last level cache MSHR in a GPU, and I see that I have an access to one, 32 byte, let's say, burst section from core 0, I say, all right, this is the tag that core 0 wanted, core 0 wants it. And then some nanoseconds later, so there's a timing aspect here, right? You happen to get lucky, and that request from core 1 comes up to your last level cache. It misses in the cache because it's not there. So then it checks the MSHR, the tag matches, and it says, I already have a request in flight for this thing for core 0. So I'm just going to mark this other piece of metadata that say core 1 also wants this. So then in effect, both of those are merged together. So you can service both with the request from the memory system. Okay. So it does not happen explicitly through some bizarre GPU in-core merging mechanism. It happens through sort of quote unquote normal CPU type merging mechanisms. And as a result, GPUs need a lot of MSHRs at both the L1 and the L2 level because you need an entry in your MSHR for every outstanding miss. Even though you've got a lot of threads, all of those threads have a lot of outstanding misses if you need 1 terabyte per second worth of memory bandwidth. So you need to have MSHRs that are able to sort of do that merging. And the problem with that is that you have to get lucky, right? Because now you're depending on the relative schedule of 2 cores running 2 distinctly different blocks. Whereas if you code your program up the right way from an individual warp, you can guarantee that you won't have a redundant access. Okay, good question. Other questions? Who remembered MSHRs after you heard that? I think it's like one slide in 565 that we sort of just gloss over. Super important in GPUs.
No, we did an entire analysis of how many MSHRs you need for.
Oh, this is the Little's law. Basically, you did the Little's law, like bottle of wine thing for MSHRs and memory bandwidth. Okay. So you should remember this, right? But the merging aspect, I don't know that we focused on the merging aspect as much, right? It's mostly just, we're assuming that you have independent requests in flight to get that bandwidth calculation. Yeah, okay, good. Other questions? All right. Okay. So let's talk about sources of inefficiency. So we talked about the thing on the left somewhat about like, okay, different warps go down different paths. But the other sort of big problem generally with GPUs is a lack of coalescing. Okay. So we call the thing when you have control flow and not all threads go through the control flow, we call that branch divergence. Okay. The other, probably even more difficult aspect of GPU programming is what we call memory divergence, where you have different threads that end up going to disparate sections of the memory system. So, branch divergence is bad because it affects your utilization of your compute units, right? You have this big wide machine and you're only using some fraction, about 132 and 132nd in the absolute worst case. Memory divergence is bad because you ended up going to memory up to 32 different distinct times to service just 4 bytes per request. Okay, so if I have a load instruction, GPU ISAs are mostly risky like ISAs, so the loads look a lot like this, which look a lot like MIPS, which look a lot like ARM, which look a lot like RISC. Okay, you basically give it an address, and then you fill that you go to the memory at that address, and then you sort of fill it into R1. But remember that like the registers are thread private. All of the threads in a warp are likely not accessing the same data from memory. They do sometimes, but that's not super useful. You usually are loading many different memory addresses to do computation in parallel on different data. That's the nature of SIMD. So they're all going to different places. If those different places are disparate in memory, like spanning the entire memory address space, then that will correspond to 32 distinct accesses to service one instruction. Okay. In the absolute best case, if all of your addresses can be coalesced into one burst section, which happens to be 32 bytes on modern GPUs, then this one load instruction will generate one memory request, one demand of the memory system. So you can have a 32x reduction in memory traffic for every load in your system if things if threads sort of fuse together in the same warp, access data that is also together inside the main memory system. Okay. Questions on this? Yes.
Doesn't this completely destroy our reduced kernel?
Doesn't this completely destroy? What do you mean?
Like the reduced kernel is kind of like fetching parts of the zones.
It depends on where it's fetching them from. Yeah, if it's fetching them from different parts of the memory efficiency of that part of the kernel is probably not very good. Sometimes it's hard to get around. This isn't always an idiot, right? This isn't always just something stupid you're doing. Sometimes it's something inherent in the algorithm itself. Graphs are notoriously hard because it's like you have no idea where you're going to go. You have no idea what node you're going to process next. It's practically impossible to keep them all together. So you soak up a lot of memory bandwidth in waste because this happens when you try to like figure out, picture a graph that's connected in, even a Facebook graph or whatever, right? You have a node and then you want to traverse and go to all of the sort of neighboring nodes of said node. The memory location of those neighboring nodes could be anywhere because it depends on the connectivity of the graph. And the only way to solve that is to pre-process it and sort them all, right? And then now you've doubled your processing time because you did a sort on it before you actually did your processing. Yeah.
For those kind of workloads, can't you have something like a trace cache or like a trace memory, where if you have already accessed some memory pattern in the graph, you just save that?
You can. That is one potential solution. It requires two things. Number one, you to re-access things because you need to see what happened the first time in order to remember to do it again the next time. And two, you need a lot of storage space because it's accessing a lot of stuff in parallel because there's 80,000 threads at the same time with their own distinct 40,000, 80,000 different node access patterns. It's kind of intractable to keep track of something like that. The solution in modern machines to make this not just absolutely terrible is to try to shrink the atom size of DRAM as much as we can, so that way we're not overfetching. But that has side effects because it makes it less efficient when things are together. It's a constant tension between trying to keep these things flexible and keep them efficient.
So is that what they do in the ray tracing code? Because ray tracing is kind of like this.
So ray tracing is special. They do a lot of pre-processing on the bounding volume hierarchy tree in ray tracing. The ray tracing core doesn't do anything magical with memory. They pre-process the, anyway, for those of you not super familiar with ray tracing, there's some data structure there that they use, and they do some pre-processing to try to keep the memory accesses coherent. In the end of the day, when you hit something and then bounce off, there's still an element of unknown in your memory access pattern. The RT cores mostly just reduce the compute you need to do when you get the memory addresses back, because there's many different, basically collision detection operations that you need to do, and it does it in a much more efficient way. But there's a whole lot of pre-processing that goes on the data structure there to try to make the memory access more amenable. Okay, other questions? All right. So these are sort of like the two biggest problems that you run into when you look at any piece of GPU code. And these are characteristics of mostly the program, right? What is the program doing? Yes, your DRAM burst size can affect how many memory accesses you touch, but if you sort of make some simplifying assumptions, really this is a program characteristic that the GPU then has to deal with. Right, so up to 32 unique different memory accesses are generated. And this can be bad even if you've got caching, right? Because now I still need to check 32 tags instead of one. So now I either have to build a cache that's got a bandwidth of 32 tags a cycle, which is insane, or I have to serialize my, now my cache basically gets backed up because I'm limited by tag bandwidth. So even if there's locality here, if they're not on that same burst length, it's still bad for the system in general. Okay, So you can figure out, based on what's going on inside array index calculations, whether your access is going to be what we call divergent or not, okay? If the, that's not entirely true. You can figure out if it's for sure going to be convergent or not. Divergent, maybe not, because it might be based on some data, right? So what are memory access? In GPUs, this is usually an access to an array, right? You've got some big array worth of data. Every thread is processing some piece of said array. When every thread goes and figures out what part of the array they want, if the equation for their index, okay, so where in the data am I going to go load this thing from? If it can be generalized to some function that is not dependent on thread idx.x, okay, so thread idx.x is the x dimension within one thread block. So for simplicity, let's just assume we have like a linear thread block. So there's 256 threads for an example. And then some function is determining where I go in A based on what thread block I'm at, maybe some input dependent data, whatever. But then afterwards, I add thread idx.x. That means that independent of whatever f spat out, I am going to get sequential accesses across every warp. Okay. So if this spits out, address, I don't know, 4480, okay, then thread 0 in a warp is going to access address 4480. Address for thread 1 is going to access what? What address is thread 1 going to access? Assuming that this is a float array. 4484, right? And then 4488, and then so on. Okay. So if the memory access or the index computation of the array looks like this, then you're going to have a nice access. You're not guaranteeing that it's aligned, right? It may still span multiple burst blocks and it might not be super efficient, but it's not going to go off into the weeds, right? It's not going to be, you may get at most, if the default is only one burst block to service a whole warp, then you'll get 2 burst blocks at most, okay? In reality, there's 4 burst blocks to service a warp in modern GPUs, but that's because of the sectoring, et cetera. They've sort of shrunk things in modern times to try to make things like graph processing better. It used to be 128 bytes, which is essentially, 32 by 4, right? So if every thread in the warp is accessing a 4-byte quantum, then it's 128 bytes. And that is the cache line size of the L1. Then they sector it down to 32 bytes, which we'll get into. But the bottom line is, from a CUDA programmer doesn't care about hardware, which is not you guys, but anyone who just wants to code in CUDA, if you access an array like this, this is good because you're going to limit the amount of, spraying across the memory space you do within one warp instruction. Okay, questions on this? No questions? It's completely clear. Yes.
How are multiple memory accesses from a few threads in the one timer?
How are multiple memory accesses from a few threads in what? What do you mean?
So all 32 threads are accessing adjacent locations, but say just the first 2 threads are accessing memory that came just before or just after. So it's still contiguous,
But it's misaligned.
yeah.
So you'll still generate 2 bursts, and the front part of the first burst will just be unused. It's nothing to do about it. It's the same when you have usually you can't do unaligned accesses in some ISAs because it makes it harder, right? For the hardware to then go fetch 2 things sometimes in one thing one time. In GPUs, they naturally have to do this because you'll happen all the time if you require some alignments. Okay, good question. Other questions? What about in between warps? Because thread IDX has nothing to do with warp, right? This is a block. So what do you think happens in between warps in the same thread block in code that looks like this? What most likely happens? Nothing? Take a guess. They access data one after another. So they're going to be discretely different memory accesses. Okay, so let's say that f function produces 0 or some, multiple 4 that's, on a 32 byte boundary. then every block around 128 byte boundary for simplicity, every individual warp is going to generate just one 128 byte block request. Okay, but then side by side warps will still generate separate requests. Okay, because they're going to access adjacent data in that array, and it can't be merged because it's actually a different block. So you'll basically have an access pattern coming out from your core, where you'll have a minimum number of memory accesses generated per warp, in the best case, just one. But then all of the warps will be generating sort of contiguous, requests, which again bodes well for the memory system, because I would load this burst and then I would load that burst adjacent to it. The memory system is mapping those to the same row of the same memory system, then you're probably in good shape. Okay, so not only does this help with sort of intra-warp coalescing to try to minimize the amount of accesses from one individual warp, it also still makes some regularity in the inter-warp memory address phenomenon. Now, at scale, that's not really true, right? Because you actually have 144 of these things, all of which probably loading some distinctly different part of the matrix, and then your last level cache sees all of it, right? And things kind of turn into a mess, and they, sort of proceed at different rates. But this is sort of the best case scenario for your GPU. This is as orderly as your program could have made it. Okay. Questions? All right. Yeah.
How much of this does the programmer need to worry about, and how much of it can the hardware handle by itself?
The programmer has to worry about this explicitly.
But if there is like really bad code, can't the hardware see that, there are opportunities for optimization?
Yeah, so we can play tricks. We can play microarchitectural tricks to try to fix code. CPUs do this all day long. GPUs do a little bit. But as a programmer, this is what you're aiming for in a GPU. Yeah.
So if you have everything in this form, then is the compiler able to figure out how to place blocks then to best align them?
No, because the compiler doesn't have anything to do with like that. There's two different systems, right? There's a runtime memory allocation system, and there's a compiler that's generating static code. So you can't, in theory, those two things could sort of work together. You could have a system that tries to, but it's kind of too hard because it depends on where the CPU is placing the data, et cetera. So it's possible, I'm not going to say it's impossible, but it's not the compiler, right? You have to have a runtime system that helps manage this too. Okay. Other questions? Yeah.
So this is like handled at runtime, and said that's the programmer has to kind of manage it. Is there a way to almost pre-fetch data and store it in the shared memory to kind of optimize this?
So usually the best written programs, and even this program, the simple optimized matrix model that we have, will try to, ultimately you have to go to main memory first. That's where everything lives. So an optimal program will try to go to main memory in this way, store it in shared memory, and then access it in whatever crazy pattern you need in the shared memory, and then move on to the next block. But at the end of the day, you always have to go to global memory for something, because that's where all the big data lives. So yeah, you're right. The programmer should manage it to not have a bunch of global memory accesses, but whenever you go to global memory, this is what you want to try to do. Okay. Other questions? All right. Where did I go from here? Now for a linear block, this is easy because there's only one dimension, but remember, CUDA has this weird thing where you can have like multi-dimensional blocks. And the way that the thread IDs actually get linearized is it basically takes the X dimension first, and then the Y dimension, and then the Z dimension. So what I mean by that is that if we've got, let me try it on the board. I never get to write on the board. Let's say we've got a thread block whose size is 1616. Okay, this is X, this is Y, all right? You have to make warps that are still 32 wide. So there's 32 threads in each warp. So every one of these threads is going to have a unique X and a unique Y. What do you think the XY is of the very first thread in the very first warp? 0, 0. It's the easy one. Okay, 0, 0, 0, 0 for X and Y. What do you think the thread ID is of the very next warp? Or very next thread? 1, 0. Okay, good. So you sort of do that. till you get to 15,0. And then what do you think happens to this guy? Then it's 0, 1. Okay. So the side effect of this is that if you've got these multi-dimensional blocks, you know, this thread IDX.X, it'll actually just repeat, right? So like if I have something that's plus TIDX.X, then, you know, you're going to get a 0 for thread 0, and then you're going to get a 0 again for thread, whatever, 16, right? Which is fine, but now it's also kind of dependent on TIDX.Y, right? Because if TIDX.Y is somehow inside your index computation, they will have different TIDX.Ys, which could result in them kind of spraying off in different places, okay? This is a subtlety that's, you know, you usually don't have to worry about all that much, but, you know, it is important to understand what's going on with these multidimensional blocks and how it ultimately linearizes everything, right? There is no three-dimensional processor. It's all linear. We just have to figure out how we map the IDs to the linear processor, okay? And then if you had an XYZ, like if you had something like ridiculous, like 222, right? Then you would basically go 0, so you go X is 0, 1, and then 0, 0, 1, 0, and then like 0, because there's a Z dimension, and then you would, you know, increment Y, so it would be this, right, 0, and then you'd increment Z and go from there, okay? Now, this thing is really stupid because the size of the whole thread block is only 2 by 2 by 2, which limits it to 8, which means that the warp only has 8. Like, then you're screwed. You can't take like stuff from different thread blocks and put them in the same warp. So this is an example of like making a thread block way too small. Questions on this? This is kind of a subtle detail. I think there's some quiz questions on it to sort of drive it home. Okay. These are just some pictures of like stuff that will be, you know, what access patterns that the coalescing engine will try to fix. So even if things aren't perfectly aligned, so I showed you a perfect piece of code where it was always plus TIDX.X, so everything's all together. The coalescer is smart enough to, like, if you're doing weird things inside, it will still coalesce them, right? So if you happen to end up on the same, you know, block or quantum, it will still coalesce them down to the minimum number of accesses. And you can also run these things as cached and uncached. So this is, you know, this is a bit of an older documentation here. If it's uncached, 32 byte is going to be your quantum. If it's cached, 128 byte used to be, but now it's all sectored, so you'd actually get 32 bytes either way. But the point of this slide is that, you know, are these lines, right? Everything I told you is still true. It's just that, you know, if they cross or you go anywhere within that one sort of, you know, range of the address space, you're still going to get good coalesced accesses. So there's hardware in there that tries to do that. And again, yeah, this is all done in hardware. If you're misaligned, it looks more like this. So if you're not caching stuff, at least in older systems, you'd get 5 different 32 byte transactions. You know, so it used to be before GPUs sectored their caches and they had 128 byte lines, you would get stuff like this, right? Where if you're just off by 1, now all of a sudden you're reading like a whole 128 byte line, even though you only needed the first float of the thing, which is a disaster, right? So this is kind of what motivated them to sector their caches and make the quantum 32 bytes, regardless of if it's cached or uncached. So I know that these slides are dated. The cache system doesn't really look that way anymore, but the modern caches, like I said, are 128 bytes with 32 byte sectors. And again, we'll cover this in some detail when we start looking at the actual hardware design. Questions on this? All right, it's mostly just what I showed you before, but from the documentation. There's a quiz online about this stuff. Okay, so let's go look at our thing, the matrix multiplication that we did. Can I not go to the next slide? Really? This is weird. Let's just do it like this. Oh, but now my thing is going to work. Okay, ignore this. Oh no. Ignore this for now. Okay. So let's go back to matrix multiplication and let's look at the access patterns we have here. So we've got 2 threads. Let's just take 2 threads as an example. the way that you go around the M matrix or the A matrix, is basically row wise, right? You're accessing things from a per thread perspective on the row direction. On the M matrix or the B matrix in this example, so the other matrix, the one you're taking the columns from, each thread is traversing it column wise, okay? And so the computation here is gonna look like, row multiplied by n plus I, where I is the iterator for the loop inside the thread. The computation over here is going to look like I multiplied by k, where I is the iterator for the thread, and then column is how we computed our column address before. Okay, but the thing to remember here is that conceptually, the threads are moving across the row in the first matrix, and they're moving across the column every iteration in the second matrix. And then here is just what each of these things is. So here's a question. All right, let's see if your intuition is true. Give me a second. Do I answer this question on the video for those of you who've already watched it? Nobody watched it. It's fine. All right. Let's see. There's two axes, the A and B here. The simple question is this. If I'm just accessing it in this way, which of these two accesses is definite coalesce? Axis to A, axis to B, neither or both. Axis to A. All right. Who thinks it's A? Be brave. I'm going to make you pick. Okay. Like maybe half the class. Who thinks it's B? 2 people? 3, 4 people? Okay. So it's B. Okay, it's B. And you're like, why? Professor Rogers, you just showed us that like this way is good, this way bad, right? Remember what I'm showing you. I'm showing you what each thread does. So every iteration of the inner loop in each thread moves in this direction or this direction. In GPUs, you don't think that way. You have to think about what parallel threads do. So if I am thread 1, okay, I am T1 and this is T2, my accesses are fused like this, okay? Because in time, yes, I'm moving down the column, but in space, among all of the threads that are fused together in these warps, I'm accessing it in the row-based fashion, right? So it's important the context here. And, if you sort of look at the computation of column in this case, right? Like, what did I tell you like 4 slides ago? If you really like looked at the math here, like this is some bunch of business that's not dependent on TID.x. This is also some bunch of business that's not dependent on TID.x. And then I just add TID.x, and that's the composition of this column, which says that when I go do the load, there's a bunch of math to figure out, well, where is the respective column of this particular thread block? That's what it's doing on this particular iteration. Then it goes .x to tell me, which column this particular thread is doing on this iteration, which is going to be by nature side by side, which is going to result in coalesced access. So it's counterintuitive from the perspective of a thread, but you can't think about single thread anymore when you program GPUs. You have to think spatially about what peer threads are doing. It's like a fundamentally different way to kind of approach your thinking of the problem versus what you're used to sequentially, right? You're forced to think in parallel to figure out how these accesses work. Okay, question? Is there a question? No? Okay. So you didn't watch the video, clearly, most of you. So this is good, right? This one is coalesce. I think I say this in the back, I can't remember. So yeah, so this part is not dependent on X, and then we added TID.x there. So, that is the good access in this pattern. This is frustrating. Okay. All right, so to sort of drive this home, right, if we look at what's going on the accesses to B, you can sort of think of it as, they're in parallel. I showed the sort of full computation here. I think I go into some more depth in the video. I don't know if I need to belabor it here. I think most of you have gotten this. But the idea here is that on each iteration, right, you're sort of moving down through, these chunks. Like there's going to be one load, right, across a whole warp that does all of this. Then there's going to be another load across a whole warp that does all of this. And that's why we get it in this nice contiguous pattern. Okay. Right. So they're going to proceed down the columns, but side by side, they actually go down the row. And in contrast, the other way is kind of terrible, right? So what happens here is, one thread is going to go access first A, and then the next one is going to access the next one and the next one, and you're going to be separated by the whole width of the matrix, right? If you think about where the parallel accesses are coming from as the adjacent, threads peel off pieces of the matrix in this direction, they're separated by the whole width of the matrix. So you only get coalescing if your matrix is stupid small, right? Where, if the row is like too wide or something, right? Then like you'll still be on the same block when you sort of move down. But in practice, real matrices, these are going to be super wide. So you're going to basically be screwed. And in GPUs, in CPUs, you might look at this and say that this access pattern done by each thread is good for what? Locality, what kind of locality? Spatial. But the downside is your cache probably isn't big enough to keep all of these blocks in the L1 long enough for it to be reused. So you're going to end up with this horrific thrashing that happens as you sort of multiplex between all of the blocks on your core. And even though there's spatial locality, you're going to generate bazillion redundant accesses to the main memory system. And this crawls your GPU program. This is like, other than, even without using shared memory, like this is like GPU performance problem number one, that you are accessing stuff in a per thread in a spatial way. And if you could have re-architected the program to do it across threads, then it would have been much better. Now, sometimes you can't. Yes.
So what observation be to transpose A so you can access the column?
Yep, that's one. But then there's an overhead because you have to pay the transpose cost. So if A is static and never changing, this is probably worth it if you do multiple computations. But then if A changes and you have to, so you pay some. You're right. If you wanted to optimize this and you didn't care about pre-processing costs, then you transpose it. You transpose it and then access in the way you like. Real matrices don't sit like this. Other questions? But there is a way to still not make this suck, okay? Because you still have to do this. Even in our optimized kernel, we still did this, right? We still were accessing the kernel fundamentally in this, I go down a row of this matrix and a column of this matrix. So how the heck did I do it without screwing up memory coalescing? And the way that this works, if you look at this code, is a phenomenon called corner turning, where I know that every block, okay, so when I do my load, remember this little piece of, this is the same piece of code I showed you on Tuesday. This was the optimized matrix model where we blocked it. So we had a bunch of stuff that loaded stuff into shared memory first, and then did the iterative computation of the shared memory, and you increase the compute intensity, right? Because you were doing more stuff inside the local scratch pad. If you drill down into the kind of mess, okay, that is the index computations of how each thread is grabbing from global memory, okay, they're not grabbing from global memory with whatever usual, the usual one that you would want it to do, right? Like when you think about, what am I doing? Right. So if you think about what goes on, when you grab from here, we're fine, right? If you're just sort of grabbing from your normal place in the tile that exists up here, you're okay. But if you're grabbing from your normal place in the tile that's over here, it's going to be a disaster because you can't, like, you have to do this on multiple iterations, right? So we're not going to do it that way. We're instead going to have them cooperatively load from this in a coalesced way. So if you look at the index computations of how we read from M and N, you'll notice that there's a plus TIDX here on this one, which is loading from the M matrix, right? So this is the bad load in the original code. And we've changed the way that we access the M matrix among the threads such that that load to main memory is coalesced across a warp. The other one is more natural because it's still the plus column, right? And the plus column naturally had the plus X there, right? So that was a nice coalesced load. So this program is an example, and I encourage you to go look at the sort of index computations here to prove this to yourself, because I've only got 1 minute left. Right? This program is an example where I know I needed a big chunk of data that all of the threads were going to chew on. So then when I went to global memory, I made sure that those loads to M and N were coalesced. Okay, because I knew a priori that I need this whole chunk. So when I do the assignment of who's going to load what, I'm cognizant of the fact of how it's actually going to get loaded by those parallel threads. And I build the index such that it's actually coalesced. Now, when I do the math, okay, when I'm doing the math, I still have to do this per thread, right? I still have to go in there and you see the, hold on. Can I do this, right? So once you've loaded it, I actually don't care how I access it because now it's on on-chip scratchpad. Modulo, there's a little bit of things about band complex, et cetera, that we'll get into, but generally, you've completely removed all of the cost of that not coalesced accesses because I'm not going to the main memory system now. I don't have this big giant burst width and a 400 nanosecond latency to go get anything. I've got it in my on-chip scratchpad. I can get at each of those elements on a 4-byte basis. I don't have to worry about burst width. So I can still access it like this and like this. So in that inner loop, right, I am still, I'm still iterating. Sorry. Just want to get this last in before I let you go. And we can come back and you guys can ask some questions on the next class. But if I look at the way that I'm accessing this little chunk of the M matrix that's already loaded, there's spatial locality here, right? I'm still like on every iteration of this loop, I'm just going to the next sequential piece, but it's okay because that's already on chip. It's sort of like a cache where you know it's going to hit because you put it in there. You know nothing is going to kick it out because it's a scratch pad, so I can sit there and do a spatial access and be sure that it's still on chip. So you're careful about how you access the global memory to get your chunk in there, and once that chunk is on scratch pad, you can access it in the natural way of the algorithm and it'll work. Okay, that's why this program is optimal, and you won't end up with poor uncoalesced accesses in this program. Questions? All right, that's it. I'll see you guys on Tuesday. Okay.